Hi everyone. Now that we understand electron affinity, we can look at two related but opposite concepts, ionization energy and electron affinity. The difference, so we have ionization energy. Ionization energy is really just the energy it takes to pull an electron away from an atom. The energy required to pull an electron from an atom or ion. Whereas electron affinity is the opposite. Electron affinity is really the atom's willingness to accept a new electron. So it's the energy gained by the atom adding in that or not always gained, the energy that the atom the energy associated with the atom taking on another electron. So associated with So with these two definitions, so we've got ionization energy is the energy required to pull an electron from an atom. Electron affinity is the energy associated with the atom taking on another electron or gaining an electron. So what we know about effective nuclear charge, as you go across your period, you have greater effective nuclear charge. So would you expect, and if you have a greater effective nuclear charge, that means each electron is being held more tightly by the nucleus. So would you expect the elements with a greater effective nuclear charge to have a larger or smaller ionization energy? So that's the energy that you need to put in to take away an electron. We would expect them to have a larger ionization energy, so it should take more energy to pull an electron from beryllium than it would from lithium, because lithium has an effective nuclear charge of 1, beryllium has an effective nuclear charge of 2, so you're having to pull an electron from a more positive atom, or from a greater, positive force. Same with boron, that's an effective nuclear charge of 3, so it should be harder to pull an electron from boron than it is from beryllium. Though there are a couple anomalies that we'll be able to explain, but that in general, as you go across the period, it's harder to pull an electron away. Conversely, the electron affinity is how much the atom really can grab more electrons. And what would you expect for that? Would you expect atoms with a greater effective nuclear charge to more easily grab electrons than those with a small effective nuclear charge, or would they be less willing to grab electrons? We would expect these elements in on the farther right of the period to have a higher electron affinity, so it's more energetically favorable for them to grab an electron than it is for these ones, because again, they have the greater effective positive charge that can drag in an electron. The exceptions to all of these, the noble gases, they're really stable, so they have a really high ionization energy and a really low electron affinity, because they really don't want to change from their present state. The reason they're noble gases is they're really stable and happy with their electron configuration. So they're not really looking to gain an electron, nor to, because if they gained an electron, it would have to go, so if argon gained an electron, it would have to go into the next energy level, into the fourth energy level, and that's a big energy jump. So it would take a lot of effort to add an electron to argon, and also if you tried to take away that electron, so it won't accept an electron. Then if you wanted to take away an electron from argon, argon is in a really stable condition. it's got a really high ionization energy because it's feeling that full +8 effective nuclear charge, and so it really doesn't want to lose its electrons. But so we've seen our ionization energy, it's increasing as you go across the period because you have a greater effective nuclear charge, so it's harder to pull away that electron. And electron affinity it also increases as you're going across the period because because of that greater effective nuclear charge. A chart in your book shows really well that ionization energy point. So you've got here you're looking at this is first ionization energy, second ionization energy. So a first ionization energy is the energy required to take away that first electron from it. Second ionization energy is the energy required to take an additional electron. Third is to take 3 electrons from the atom, or to take that third electron from the atom. Fourth ionization energy is to take that fourth electron from the atom, etc. So we'll look at this in combination with our periodic table. So we'll start off with sodium, a group 1 element. So it's got a pretty low first ionization energy. You can see it's lower than all the others within. This is looking just across period 3. So each of these going down in this table is one further to the right in the on the periodic table on period 3. So sodium, it's got a really low first ionization energy. It's really easy to take away that 1 electron from sodium because its effective nuclear charge is only 1. But then if you look at the second ionization energy, it's significantly larger. So you went from 495, what are these units, kilojoules per mole, to 4,562 kilojoules per mole. And that's because, if you remember that the chart we made last video, this one, its effective nuclear charge is 1, but these have an effective nuclear charge of 9. So those are all of a sudden being held much tighter, so they're much more, those core electrons are very stable, and sodium's not really willing to part with those ones, but the outer electron, that's only an effective nuclear charge of 1, so it can take it or leave it. Well, more leave it. It won't take it. And we'll see when we do the electron affinities. Sodium really doesn't like adding electrons. It mainly is going to give up electrons, which will be important when we get to ionic bonding. Magnesium, it has those 2 valence electrons because it's that group 2 element. So it has the first ionization energy. It's larger than sodium's because it has that effective nuclear charge of +2 for each of the valence electrons. So it's hard to grab that first one away. And then the second one, it's even higher ionization energy to grab magnesium's second valence electron, because now you're pulling an electron from a positive ion, so you're taking away a negative charge from a positive ion, and so it's hard to do because there's a large attraction between them. And you see again this jump as you try and start taking the core electrons. You'll see atoms don't like giving up their core electrons. They don't like getting out of that electron configuration. Looking at now aluminum, where we've got 3 valence electrons, and so you can see it's steadily increasing ionization energy, but again that big jump as you get to the core electrons. Looking up this first ionization energy, it gets increasingly large as you go across the period, and that's because the effective nuclear charge is, like, by the time you get to chlorine, that effective nuclear charge is +7, so it's much larger. And it's not. When we're looking at ionic bonding, we'll see that these large values of ionization energy aren't balanced out by other atoms trying to gain those electrons. So these ones later in the period, would you expect them to be more willing to lose or gain an electron? Well, we haven't looked at the energy associated with gaining an electron, so we'll put that question on hold. But so now we've seen that for ionization energy, the energy required to take away an electron, you've got much lower ionization energy in the group 1 area, and it increases as you go across the periodic table. We'll look more at the transition elements in a little bit. They don't change as much as the main group elements. You can see in this figure in your book, they're a lot closer together. But you remember, they're filling in their d orbitals, which are a level below the valence level, so they're not really as there's not as much of an effect for them. You can see these dips in the ionization energy, and we'll go ahead and talk about those now, because it's going to be that same pattern on the electron affinity. So when you're looking across, this is a chart showing the trend in the first ionization energy. So we'll ignore, we won't ignore anything. So lithium, going from lithium to beryllium, you've got that expected increase in ionization energy, but then your ionization energy decreases going from beryllium to boron. But remember, in the quantum mechanical model, you've got, this is your S block. This chart is omitting all the transition elements, so it's just the S block and the P block. So here, going from beryllium to boron, you're going from your S orbitals to your P orbitals. And because remember that the P orbital is higher in energy than the S orbital, so adding an electron from, taking an electron away from from boron, puts it back into a lower energy state, because it's going from that higher up atoms. Remember, the electrons like to be in the lowest energy state possible, and P is a higher energy orbital than S. So getting rid of that one P electron is pretty energetically, it's favorable energetically. So that's why boron has a little bit lower ionization energy than beryllium, because you're dropping back down to a lower energy state. It's the same reason the group 1 has a low ionization energy, because then you drop back down to the energy level of the period before them. So then you have the expected increase in ionization energy. Then you have another dip at the about 4 into the P block. And remember, on your orbital diagrams, we'll draw a P orbital diagram. So this is just looking at the P orbital. You've got your first electron, and so that would be like boron's electron right here. Then you get to carbon, then nitrogen. And then in order to get to oxygen, you have to put an electron, you have to start doubling up the orbitals. But remember, electrons don't like being beside each other. And so that's why you've got a bit of the dip in energy here for ionization energy, because oxygen will let you take away that electron more easily than nitrogen will, because it gets rid of it having to double up. It'll let it go back into that just one electron in each orbital, satisfying that Hund's rule. It doesn't really like doubling up the electrons. And then it just finishes out the table as we would expect. When we look at electron affinity, we're going to see that so the anomaly is in the same place. So it's really group 13 and group 16. And that's because this is where you've got an electron in the P orbital, and so that's in a little bit of a higher energy state, and this is an electron starting to double up in the P orbital, and electrons don't really like that. So our electron affinity is the energy it takes to add in an electron. And like the ionization energy, it's pretty consistent going across the period. So you can more easily add an electron. We'll look again at this chart, or this is a different chart, but it's still just the main group elements. We're ignoring transition elements. So this, a negative number means that energy is released with the element, with that element adding an electron. So it's something that could happen. Positive value, so if the number is greater than 0, then it won't add in an electron because it would take energy to put it in. So electron affinity is an exothermic process. Its energy is going to be released as the electron gains itself. So beryllium's not going to gain an electron, and again, that's because it's already got its s orbital full. It doesn't want to jump up to the next orbital. It doesn't want to jump up to the p. Same with nitrogen. Nitrogen is positive because it doesn't want to have to start doubling up its electrons. The other ones in group 15 are group 15 here. Sorry, up here can add on electrons, and same here. Though magnesium also can't, calcium and strontium can. But you see these, it's not really an energetically favorable thing. Not like with fluorine, which will very readily add in electrons. You may have noticed from looking at these numbers that this negative 328 doesn't fully compensate doesn't fully compensate sodium's ionization energy. That's only 495, whereas this fluorine's 328. So it's releasing 328 by adding in an electron, but it takes 490 to get rid of sodium's electron. And we'll get into in class what makes up that energy difference, why the bonding still happens even though this process doesn't adequately compensate sodium for giving up its electron. So that's the electron affinity and the ionization energy. Those are the two main concepts that will be really important for knowing how ionic bonding will happen. And we will get into ionic bonding in class on Monday. But that is that.